In the last section, we looked at roots of quadratics, and we said that a quadratic has no more than two distinct roots. And if a root is a non-real complex number, then they occur as a conjugate pair. So that means, for example, if we had a quadratic and one of the roots was 2 plus 3i, then we know that straight away one of the other roots of the quadratic must be 2 minus 3i. And actually these have to be the only roots because a quadratic can't have more than two distinct roots. And we also had this extra condition that a, b and c had to be real numbers. And that just meant that the coefficients a, b and c had to be real. They couldn't have I in them. So it turns out that this is true for any polynomial, not just a quadratic. So if you've got a polynomial, f of x, or f of z, and it's got real coefficients, if z1 is a root, then its complex conjugate is also a root. So this is really useful for factorising and solving cubics. So before we have a look at the example, let's have a look at what the different possible cases are for the roots of a cubic. So we could have a cubic which has three distinct real roots. For example, the roots could be 1, 1, and 1, 2, and 3. You could have a cubic with roots, only two distinct roots. So that would mean that one of them has to be repeated twice. So for example, you could have a cubic which is 1, 1, and 3. And that will mean that the cubic will touch the x-axis at 1. A cubic could also just have one distinct real root, and that would mean that the root's repeated 3 times. The easiest example would be 0, 0, 0. And an example of a cubic that's like that would be f of z equals z cubed. If you were to draw a sketch of z cubed, it would look something like that, and it would go through 0. And that's why it only has that one root, which is 0, which is repeated. Well, these are the examples of when you've got real roots. Let's look at what happens when you've got a complex root. So if we know that we've got a non-real complex root, so for example, we could have 2 plus 5i, then we know as long as the coefficients in the cubic are real, then the other root is going to be 2 minus 5i. Well, a cubic has to have 3 roots. We can't have a repeated complex root, so the other root must be a real number. So for example, you could have the other root as 3. So this is the only possible case: a complex conjugate pair and a real root. Just one real root. What's impossible would be something like this. So it would be impossible to have 2 plus 5i, its complex conjugate 2 minus 5i, and then the third root being another complex number, a different complex number. For example, 7 minus 2i. The reason why that's impossible is because we know that if 7 minus 2i is a root, then 7 plus 2i is also a root. Now this is impossible because a cubic can have at most 3 different roots. So this is impossible because this has 4 different roots. So it can't be the case that the third one was a complex number. It has to be a real number. So let's have a look at example 10. So we've got this cubic equation, and we're told that minus 1 is a solution. So to find the value of k, we can just substitute in z equals minus 1 like you normally would. So we know that minus 1 cubed minus minus 1 squared plus 3 times minus 1 plus k is equal to 0. So if we solve that, we'd get k is equal to 5. In part B, we're going to try and use this fact to find the other roots of the equation. So our aim is we're going to try and take this cubic, which we don't know how to solve at the moment, and we know k is 5. And we're going to try and factorise it. Well, we know that because minus 1 is a root, that z plus 1 is a factor. So our aim is to factorise this and take z minus 1 outside of a bracket. Well, in order to get a cubic, we know that we're going to have to times this linear factor by something with z squared in to get the z cubed term. So we're going to have a quadratic here. And our aim is to try and find out what that quadratic is, because then we'll be able to solve the quadratic equal to 0 to find the other roots. So I'm going to do 3 different methods, and sorry about that, but I don't know which method you prefer. So the 3 methods that I'm going to use are long division, grid method, and comparing coefficients. Feel free to skip forward if you're confident with polynomial division, which I imagine you are. So with long division, you would do z plus 1 on the outside, and we're going to do this cubic divided by z plus 1 in order to end up with the quotient, which is this quadratic. So we're going to put z cubed minus z squared plus 3z plus 5. So we're going to say, what do you have to times z by to get z cubed? Z squared. Then we're going to times everything on the outside by z squared. So we're going to do z squared times z, which is z cubed, z squared times 1, which is plus z squared. Then we're going to do the top line, take away the bottom line. Z cubed take away z cubed is 0z cubed, minus z squared is minus 2z squared. Really, we've got 0z here and plus 0. So 3z take away 0z is 3z. 5 take away 0 is 5. And then we're going to repeat that process. What do you have to times z by to get minus z squared? Minus 2z. And then times minus 2z by everything on the outside. So we get minus 2z squared. Minus 2z times 1 is minus 2z. And really, we've got plus 0 there. Top line take away bottom line, these ones cancel. 3z minus 2z is 5z. 5 take away 0 is 5. And then repeat the process. What do you have to times z by to get 5z plus 5? Times 5 by everything on the outside. 5 times z is 5z. 5 times 1 is plus 5. And then do the top line, take away the bottom line, and we get 0. So that shows that our remainder is 0, which is good because we know that z plus 1 is a factor, so it factorises in perfectly. So that tells us that the quadratic is z squared minus 2z plus 5. Grid method, we're going to use the fact that we know that if we times z plus 1 by the quadratic, then we have to end up with a cubic. So we're going to do z plus 1. That's representing z plus 1. And we're going to multiply it by the quadratic. So along the top here, we're going to have az squared plus bz plus c. So az squared plus bz plus c. And when we multiply these two things together in a grid, we want to end up with the cubic. So az squared times z has to give me z cubed. So I want z cubed here when I multiply these two things together, because that's my z cubed term. So I know that I'm going to have to put z squared there. So when I multiply these together in a grid, I know that I'm going to have z squared there. I'm going to get my z squared terms by adding together these ones here. So I'm going to have z squared plus something, and I want to end up with minus z squared. So I'm going to have minus 2z there, minus 2z squared. So I know that I need minus 2z in that box there. Minus 2z times 1 is minus 2z. I'm going to get my z term by adding together these two when I do my grid multiplication. So I want 3 z's in total, so I need to add on 5 z's to make sure that I have 3 z's. So I know that I need plus 5 there. 5 times 1 is plus 5. And that matches my plus 5 there, which means that z plus 1 goes in perfectly without a remainder. So I get my quadratic the same as before. And then finally, a method that we're going to use a lot in further maths is comparing coefficients. So I'm going to quickly do this method as well. So comparing coefficients, we know that z cubed minus z squared plus 3z plus 5 has to be identical to, and then I'm going to expand the right hand side. So we're going to have az cubed plus bz squared plus cz plus az squared plus bz plus c. And then in order to help us compare coefficients, I'm going to group together the z squareds and the z's. So we've just got az cubed, and I'm going to take z squared as a factor out of these two z squared terms. So we're going to have plus a plus b z squared, and plus, I'm going to take z out of the z terms, so b plus c z, and then we've got a constant term c. So to compare coefficients, let's compare the z cubed terms. We've got 1z cubed on the left hand side, and we want that to be the same as az cubed. So we know that a has to be equal to 1. Next, we can compare the z squared terms. So we know that minus 1, that's our coefficient of z squared on the left hand side, is equal to the coefficient of z squared on the right hand side, a plus b. Well, we know a is equal to 1, so we can solve that to find b equals minus 2. And then finally, to find c, we could either compare the coefficient of z, so 3 equals b plus c, but even easier, you can see that our constant terms have to be the same as each other, so we know that plus 5 has to be the same as plus c. So we know that c is equal to 5. So with all these methods, we get the same quadratic. We get that that's equal to z plus 1, and then our quadratic is z squared minus 2z and plus 5. So all that remains to do is solve this equal to 0. That was our original aim. So we know that either z plus 1 is 0 or z squared minus 2z plus 5 is 0. Z plus 1 equals 0 just gives us the original root, z equals minus 1. So we're going to solve z squared minus 2z plus 5 is equal to 0. So you can use whichever method you prefer. I'm going to use the quadratic formula. So we're going to have minus b plus minus the square root of b squared minus 4ac all over 2. So we're going to get z equals 2 plus or minus the square root of minus 16 all over 2. And then I'm going to write this as, I'm going to split this up into two fractions. So we're going to have 2 over 2 and plus or minus root minus 16 over 2. Root minus 16 can be split up into root 16 times by root minus 1. So that's equal to 4i. So we're going to have z equals 2 over 2 is 1 plus or minus 4i over 2. So that simplifies to 1 plus or minus 4i divided by 2 is 2i. So we're going to finally write down what our roots are. So the roots of the cubic were minus 1, 1 plus 2i, or 1 minus 2i. And notice that we've got this complex conjugate pair like we must have.